So what I was telling you here is that if you have an amplifier, generally it's a two-port device, which means it has four terminals. So two terminals at the input and two terminals at the output. I also said that the one terminal is common between both the input and the output. So that shared terminal, I'm calling it as the common ground. So input and output, these are two terminals, and so totally the device then becomes a three-terminal device. This can be a voltage amplifier, current amplifier, transconductance amplifier, or a transresistance amplifier, or a transresistance or transimpedance. So in all the four cases, typically the device turns out to be a three-terminal device. Okay, so your BJT, MOSFET, this amplifier can be your BJT, MOSFET, or a vacuum tube amplifier. All these devices end up having three terminals. Okay, so now what we are going to do is, in the previous lecture, what did we do? We replaced this amplifier by its equivalent model. We found out input resistance. So input resistance is the effective resistance seen at the input of the amplifier. So that's what I've written here. So this is the source, okay, BS modeled resistance and voltage source and resistance modeled in series. That's your voltage source. So we discussed why do we actually model a resistance in series with the voltage source? What was the reasoning? What does the series resistance capture? What does the series resistance and a voltage source capture?
Internal resistance.
Yeah, internal resistance, and more, what does that signify? I mean, when I model as a, I mean, does it makes the model more practical? How do you quantify? Internal resistance is fine. Is there something more than that? Limits current, yes. The max output ability. So when you say output, what do you mean? Power. Power is what we are talking about, right? That's the most important thing. So what did we say? If you, let's say, for example, a microphone, what I'm speaking right now is converted to an electrical signal by a microphone. A microphone, let's say you are a circuit designer and you are supposed to design an audio system. What will you do? You are going to model your microphone as a voltage source. But this model is absolutely incorrect. Why is that? What is the problem with modeling a microphone as a voltage source?
So the maximum power by a microphone is very small.
Maximum power delivered is very small, but if you assume an ideal voltage source, the definition of an ideal voltage source is what? It can provide infinite power. It can provide infinite power. Okay, that's the ideal definition. But that doesn't capture what's happening in reality. In reality, a microphone will be able to deliver only a few microwatts of power, or a few milliwatts or microwatts of power. So then what do? We model a source resistance Rs. Then this limits what is the maximum power this voltage can deliver. Now what is the maximum power this voltage source can deliver now if I model a source resistance? What is the value? Can I say it is Vs squared by 4Rs? This is the maximum power this source can deliver. Okay, so that's the reasoning behind the modeling of source resistance. Similarly, by Thevenin Norton equivalent, by an equivalent Norton representation, I can convert a voltage source and resistance in series to a current source and resistor in parallel. So one of you are asking, why does the resistor, why do we have to put a resistor in parallel? In case of voltage source, we are putting it in series. One way is directly to look at it from Norton to Thevenin equivalent. So there is something called terminal equivalence. Let's say we have a device. You want the device to look the same between the two terminals. So then these two circuits are called terminally equivalent, meaning you can show that the behavior of these two circuits will be same if I short circuit these two terminals and measure the current, or if I open circuit these two terminals and measure the voltage. If I ensure that they both are same, then these two circuits, we can say they both are terminally equivalent. Rs is the internal resistance of the voltage source. Rs is the internal resistance of your battery or voltage source or your microphone, all that, that's what I said. So therefore, equivalently I can say this. Or even if you don't want to go that way, let's start from, is my voice breaking?
No, sir.
Okay. So even if you don't assume that, let's assume you are going to model your source as a current source. I gave you an example. What is an example of a current source? A photodiode. Let's say you're an engineer who's modeling the receiver of a fiber optic cable system. In a fiber optic cable system, the receiver typically consists of a photodiode, which converts light energy to electrical energy. It converts light energy, signals of light, to electrical energy. And we said a photodiode, the way in which it operates is that it converts light signals to equivalent electrical current signals. And that's why we said we can model a photodiode this way as an equivalent current source. Again, photodiode has a maximum limitation. It can only deliver, it's a weak power, it can only deliver few microwatts of power. So if I model a photodiode as a current source, an ideal current source by definition can deliver infinite power. That's what we discussed in one of the previous lectures. So therefore, this model is also not accurate. So we have to include some kind of, you have to limit. For example, let's say I connect a load resistance across this. If I connect a load resistance across this, what do I mean by infinite power? The power delivered to this load resistance is I square R into I square into RL. So if I make RL to infinity, if I keep a very large resistance in parallel, if I connect it, then by this model, this is the model I'm going to use for my photodiode. By this model, it looks as though this model says that the load resistance can extract infinite power out of this model, out of this photodiode. Because if your RL is infinity, even then you will be receiving the same current. That is not right? So as your load resistance increases or decreases, the current that it is receiving should change. So therefore, to model that, one of you are asking why not put a resistance in series? And we said that doesn't make any sense, because even if I put the resistor in series, the current that is going to flow out of RL will always be IS. That's not going to change. Okay, so therefore the power will always be I square RL. So even though I'm modeling this as a series resistor, it really is not a right model. So we have the other ways to model it in parallel. You have to model a resistor RS equivalent source resistance in parallel. Now in that case, if I ask you what is the maximum power now you can deliver, see, remember, a voltage source and resistor in series is equivalent to a current source and resistance in parallel. So now if I add a source resistance in parallel with it, what do you think is the maximum power this current can deliver to the load resistance now? See, use Thevenin equivalent and quickly you can say, see, by Thevenin equivalent, I can represent this as what? Vs, what is the value of Vs if I use a Thevenin equivalent for this current source and resistor in parallel? You have a current source and resistor in parallel. Vs equals, yes, it is ISRS. So it is, can I say it is ISRS? So it will be ISRS the whole square by 4. That will be your total power. Okay. So ISRS, see, RL equal to RS. That's when maximum power transfer happens. Yes. So the whole idea is that if I model a resistance in parallel with a current source, or a resistance RS in series with a voltage source, both of them models the power delivering capacity of the source. Okay. So they model the maximum power that the source can deliver. Okay. I'm sorry, this is IS square RS by 4. Okay. So this is your total power that can be extracted out of it. That's it. So this is what we are modeling in by putting current source and resistor in series in parallel. So now let's come back to the amplifier model. So this is the amplifier model. I'm going to take this amplifier. First, I'm calling it as a voltage amplifier. A voltage amplifier is one which amplifies voltage. Output quantity is voltage, input quantity is also voltage. Now, this, as far as the input is concerned, I can replace the input of this amplifier by an equivalent resistance Rn. And the output is, it's a voltage amplifier, therefore it's going to be a dependent source model. At the output, it's going to be A times V in, AB times V in. Okay. At the output, I'm going to represent it by a dependent voltage source of value AV times V in, and similarly let R out with the output resistance, which I'm measuring at the output terminal. Then I'm going to put that R out in series with the output source. See, whenever your dependent source is a voltage, output resistance should be in series with it. Okay, the same arguments go for it. The Thevenin representation. That's like a Thevenin representation. Okay, so this is your mathematical model for an amplifier, a voltage input, voltage output amplifier. Input is represented by a resistor. So that is your input voltage. The output port is a dependent voltage source, AV times V in. AV is the gain, and R out is the output resistance. So this is your two-port model. I told you guys sometimes we may be shorting these two terminals and it will become a three-terminal device. So this is your mathematical model for the voltage amplifier. Now let's try and find out the overall gain of the amplifier. See, I am now connecting a load resistance and there is also a source resistance. We will now see what will be the overall voltage gain of this amplifier. Why it is AB into VN? Okay. So in the previous lecture we said there are 4 types of amplifiers: voltage amplifier, current amplifier, transconductance amplifier, and transimpedance amplifier. So if an amplifier input is voltage Vn, the output voltage, if it's a voltage amplifier, we are going to assume the voltage gain V out is AB times Vn. Okay, this is the mathematical model of the amplifier. For an amplifier, yeah, it's an AV times Vn. And similarly, we can measure output resistance and replace the model with a resistor in series. Now I'll define what are these individual terms in more detail, and you will also appreciate and understand why do we need Rin and Rf. So let's derive the overall expression. See, this is Vs is the input, Vl is the output. Okay, what is AV? AV is the gain from this point to this point. AV is just the gain from this node voltage V0 divided by V in. So the input of the amplifier, the gain from this point to, there is an internal node in the amplifier. So this is some internal node in the amplifier. It's still that point. But we are interested in finding out from the input source Vs to the load voltage VL. So we are supposed to find load voltage divided by the input voltage Vs. Okay, so how do we find that? We can do this in a step-by-step process. First, find the voltage V in. So I can find it this way. VL by Vs can be written as V in by Vs into V0 by V in into VL by V0. So now if you see, everything will cancel out and this will be equal to VL by Vs. So we will go step by step. So what is V in terms of Vs? Look at this. This is simply a resistive divider. This is a resistive divider network. So what will be voltage V in? Rn by Rn plus Rs. Is that okay? So if it's a potential divider network, if it's a potential divider network, I think, see guys, this I can assume you are aware of, right? You should be able to, potential divider is like in memory, right? Yeah, okay. So your input voltage V in can be written as Vs into Rn by Rn plus Rs. So you are now at this point. You have now come to V in. Next, your V0 voltage, V0 is simply multiplied by AV. So if I multiply it by AV, this voltage, what I'm going to get is V0. Now once you know V0, again if you see from V0 to VL, there is again another potential divider. So this is V0, which is AV times VL. So AV times VL equals V0. There is another potential division. The potential division is RL by RL plus R out. So that's what you get here. So now multiply all the three. This will be your total expression for the output voltage in terms of the input voltage. So your load voltage at the load resistance is Rn by Rn plus Rs multiplied by the AV. With this AV, it's called as the unloaded or intrinsic gain. I'll come to what does it mean. We'll again define it. And finally, the output loading. So this is the reduced factor because the output terminal because of finite output resistance. Now look at this. What do you think is the maximum value of this VL by Vs? What do you think will be the maximum possible value of VL by Vs? See, assume that for the time being Rs is 0 and RL is infinity. So I'm open circuiting the output node voltage and Rs is 0. input resistance is time being for its ideal source, assume that it's 0. What will be the maximum gain? AV, yeah, it's right, your AV. No, it won't be AV by 4, it will be AV itself. AV is the maximum voltage. Yes, I think someone wrote AV by 4. This course, we will not be dealing with power transfer. Purely, I'm asking what is the maximum voltage gain possible. AV by 4 is a very different concept. We'll come to that later. Right now, you can see if I use these conditions, RS is 0 and RL is infinity, the maximum possible attainable gain is AV. That's the maximum voltage gain you can get out of the system. Okay, that's why it's called the intrinsic gain or unloaded gain. When I say unloaded, what do you mean? There is no loading from the source side, which means I'm assuming source is perfect. And there is no loading from the load side, which means there is no load at all. I've made the load as infinity. So this is called no loaded, unloaded gain. You are not loading the amplifier either at the input side or at the output side. So these two factors, Rin by Rn plus Rs, Rout by RL by RL plus Rout, these are called input and output loading terms. Because of amplifier's finite output resistance and amplifier's finite input resistance, I mean voltage source's finite input resistance, okay, your gain will reduce from its maximum attainable value. Now let's assume Rs and RL are not infinity. See, in real system, Rs and RL are never infinity. I mean, RL is never infinity and Rs is never 0. But still, if I want to maximize the gain of this amplifier, as an engineer, if you had the freedom of choosing R in and R out, what will you choose those values to be? Look at this equation. I want this value to be 1, this value to be 1. Let's go with this one. If you want this term to be 1, what will you choose? Okay, so can you explain AV again? AV, it's called as the unloaded voltage gain. Unloaded voltage gain means feed Rs equal to 0 and RL equal to infinity to this amplifier. Make sure this, so this is the AV, it's called unloaded voltage gain. That's the maximum gain you can get out of this amplifier. You can never get a gain greater than AV from this amplifier. It's called as the intrinsic gain or the unloaded voltage gain. Unloaded voltage gain of the amplifier. See, it's a voltage amplifier. You just take a voltage amplifier, you apply an input voltage, and you take the output voltage without connecting any load, or don't connect any load and don't connect any input source. Just directly apply at the input terminal of the amplifier and then measure the voltage at the output. The gain you get out of this, the ratio of V0 by Vin, it's AV. Okay, that's the that's how you define AV. Okay, so now I'm just asking you guys, max can R out, but is infinite gain possible? Okay, it's not a gain, infinite resistance. I think you're asking infinite resistance. Okay, yeah. So I'm just theoretically asking you, as an engineer, if your goal is to ensure that you want to get maximum voltage gain out of a voltage amplifier, then you will choose Rin to be infinity. If you choose Rin to be infinity, this term will become 1. And if you choose RL to be Rout to be 0, then this term will be equal to 1. So for an ideal voltage amplifier, you'll have to satisfy these two conditions. Rin will be infinity, Rout should be equal to 0 or as low as possible. Okay, this is an ideal voltage amplifier. So for an ideal voltage amplifier, it doesn't matter, the gain is independent of Rs and RL. Okay, it will always be equal to AV itself. Right? If the voltage gain, these two terms will be 1. This term will be 1. This term will also be 1 for an ideal voltage amplifier, because Rin is infinity. Rin by Rn plus Rs will be equal to 1 in that case. And if Rout is 0, RL by RL plus Rout will also be equal to 1. So this is an ideal voltage amplifier model. Okay, so that's the definition of an ideal voltage amplifier. So as an engineer, if you are supposed to design an ideal voltage amplifier, you have to keep in mind you will aspire to design a very high input resistance and a very low output resistance. This is what you will do. Okay, then I'll discuss one more amplifier model. This is the most commonly used model. In fact, this is the only model we will be using throughout this semester. It's called the transconductance amplifier model. So what is a transconductance amplifier? A transconductance, let's take a two-port model of an amplifier. In a transconductance amplifier, I'm going to apply a voltage as an input, and then I'm going to measure the current as the output. The ratio of I out by V in is what we call transconductance. Okay, so we distinguish, you know the difference between conductance versus transconductance. In transconductance, you apply input at one terminal and measure current at some other terminal. Then we say the transferred conductance to that terminal is the ratio of the current at that measured at the other terminal divided by the input voltage. So that's called transconductance. In a similar way, for a transconductance amplifier, we can model input resistance and output resistance. So look at this, input resistance is same. Between the two input terminals, I replaced it with a resistor of value Rn. What is the value of Rn? If you are asked to find Rn, you apply a voltage Vin and measure the current flowing into the amplifier. Then Rn will simply be equal to Vin by In. This is Rn. Okay. So typically I said when you are measuring Rn, typically you keep the load resistance alive. You keep the load resistance as it is at the output terminal. Okay, that's how you measure Rn. Then if you want to measure Rout, what do? You will short circuit the input. Usually we keep the source resistance as it is and short circuit the input and apply a test voltage here, Vx, and measure the current that's being drawn into the amplifier.
So can you discuss about Rn from Rn actually?
Yeah. So how do I measure Rn? So you take, it can be any amplifier, transconductance, voltage amplifier, any amplifier. It's a two-terminal device. What should you do? Remove your input source completely. Remove your input source completely. Then keep your load resistance as it is. Keep your load resistance as it is. And then, see this part you're removing completely. And then I'm going to apply a test voltage here. You can call it Vs or Vx. Test voltage Vx or Vin, anything, it doesn't matter. And then measure the current Ix drawn by the amplifier. Okay, the ratio of Vx by Ix will be your input resistance. See here you have to keep your load active as it is, and the ratio of this will be input resistance. Guys, don't worry, it will become more clear when we solve circuits. I'll probably solve circuits in, I don't know, maybe I'll post some videos or I'll solve it in Saturday. So you will understand, don't worry, in fact for the next 10-15 lectures we will only be doing this. We'll take some different circuits, keep on finding Rn. So it will become more clear. But on general procedure, what I'm saying, keep your load resistance as it is, apply a test voltage and measure the current drawn at the input of the amplifier. Then the ratio of Vx by Ix is Rn. Similarly, short circuit your input, make your Vs go to 0, so your Rs will be present. Now remove your load resistance. When you are measuring output resistance, remove your load resistance, apply your test voltage source Vx and measure the current Ix drawn at the output terminal. Then the ratio of Vx by Ix is what we call the output resistance. So it's see this is a transconductance amplifier. For a transconductance amplifier, input is voltage, output is current. So whenever I'm modeling the output resistance, because output is current, I have to put it in parallel with the transconductor source, the current source. It's a voltage dependent current source, right? In a transconductance amplifier model, the output current is a voltage dependent current source. So it will be GMVN is the transconductance. An ROut resistance will appear in parallel with the current source, and it will also appear in parallel with the load resistance. So now can we quickly derive what will be the overall? See, what is the quantity of interest? Let me call the quantity of interest previously was current. Okay. Generally, what we get from the MOS amplifier or BJT amplifier is a transconductance amplifier. And we use this transconductance amplifier as a voltage amplifier. That's what we will be doing. By nature, naturally, if you see MOS amplifier or a BJT amplifier, okay, we never get them in the form of a voltage amplifier. See, mathematically, if you model a BJT or a MOSFET, it will never reduce to a model like this. Okay, but it will, if you actually mathematically model your MOSFET and BJT, it will reduce to a model like this. But eventually, what is the goal in this course? We have to design voltage amplifiers. So therefore, I am going to use my transconductance amplifier itself as a voltage amplifier. So let's derive the output voltage divided by input voltage. What we have to put RS in the input to find out. Yes, you have to keep RS. That's the most accurate way of measuring it. If you want to accurately measure output resistance, then you have to keep RS in the circuit as well. Okay. See, generally, look at this model. Look at this model mathematically. If you look at this model, if I ask you to find R out from this model, how will you find? Remove this load resistance, and you'll apply a test voltage Vx and measure the current Ix flowing into it. Now, what should we do? We should also short circuit the input voltage. Now, if I short circuit the Vs, what is the value of V in here? Vs is short circuit, right? V in, yes, 0. Is that okay? V in is 0 because why? What is V in? V in is simply Rn by Rn plus Rs into Vs. So Vs is 0, V in is also 0. If V in is 0, then this current source is also 0. This is also 0. Then I can remove the current source. I can open circuit the current source. So what is the output resistance seen here? What is the value of the output resistance? Okay, so the output resistance is R out itself. From this mathematical model, it is R out itself. That's it. So that's how we find. So to find accurate calculations, we must know one of the two values to find the another. I didn't understand that. What do you mean by that?
Sir, I meant we should either know our input or our output to find the either of them.
No. RL or RS. No, not RN or R out are independent. You don't need to
Yes,
know
sorry, RS and RL.
Yes. You need to know both. Okay. In this example, what I am showing now, in this example, it doesn't depend on RS and RL. Mathematical model for this, but we will take circuits later, and we will see that RS and RN will R in and R out will have dependence on RS and RL. In the circuit model that I have drawn, there is no dependence. That's what I'm trying to say. Okay, just be patient, guys. You will understand it. What I'm trying to say here. I think once you solve an example, you guys will understand it. Okay, just be patient. We have one more lecture. I'll take you through that. So now the voltage, we'll try to derive the output voltage V0 by Vs. Okay, let me call this, instead of V0, let me call VL. So can you quickly say what will be V in by Vs? V in by Vs is simply Rn by Rn plus Rs. That's the first step. It's a straightforward, you can write that. Now the next is, let's try to write the output voltage. Okay, here I've written it as V out. So okay, let me just keep it as V out or V0. Your output voltage, look at this, it's a current source. Can I say these two resistors are in parallel? So you have a situation like this. You have a current source of value GMVN flowing through a parallel equivalent of R out parallel RL. So now look at this circuit. If you are asked to find the voltage, this is the voltage at this point. So can you directly say what will be the voltage? You can directly do a Thevenin representation and find the open circuit voltage. That's also fine. Or you can apply KCL at this node, Kirchhoff's current law at this node. So you will get V0 by R out parallel RL, that's the current flowing through this, plus GM times Vn equals 0. From that, you can directly derive this. So your output voltage is minus of GM into R out parallel RL times Vn. Okay, see, but in this course, I don't expect you to write KCLs and KVLs and derive it, but intuitively you should directly see it in terms of currents flowing in circuits. You have a current of GMVN flowing in this direction. I can then simply replace this with a current minus GMVN flowing in this direction. Now visualize this way. I see it as a current flowing. Now I'm seeing this current flowing through the resistor. This is the path in which it is flowing. So the voltage drop across the resistor is output voltage itself. So it's minus GMVN into R out parallel RL. That's it. So this is the way we'll have to slowly start understanding it intuitively, so that you don't have to write an equation like this. And see, in exams, now that all exams are open book, we don't even expect you, even in your on-campus exams, we never expect you to write KCLs and KVLs fully. Okay, even if you wrote it by intuitions, we are fine with that. Okay, so that's your output voltage is written in this format. I'll expand this term R out into GM into R out into RL by RL plus R out. Then I'll remove this term and write it this way: minus of GM R out into RL by RL plus R out into Vn. I will substitute Vn by using this equation, Rn by Rn plus Rs into Vs. So then I get the output voltage in terms of the input voltage as Rn by Rn plus Rs into minus GMR out into RL by RL plus R out. So here for this amplifier, the intrinsic gain or the unloaded gain happens when, see, look at this. This is an transconductance amplifier. For a transconductance amplifier, if I make Rs as 0 and RL as infinity, what is the maximum voltage gain you can get out of this amplifier? Rs is 0. I am making this as 0. So I am short circuiting this. So can I say Vin is Vs? So this is Vs itself. So here you get Gm into Vs minus, the sign is very important, minus Gm. See, because the current source is pointing downwards, so it is minus GMR out. Okay, here the polarity fine. So it will be minus of GMR out. The magnitude is plus GMR out, but it is intrinsic gain is this. This is the maximum gain you can get out of this amplifier. Okay. Otherwise, I already told you guys that for any real amplifier, you can never have Rs to be 0 and RL to be infinity. Generally, they will be finite. Okay. So for example, I told you guys most of your loads can be modeled as a resistor. A loudspeaker, an audio speaker can be modeled as a resistance. On a cell phone, you will be designing an amplifier which will be driving an antenna. An antenna will, on your cell phone there is a handset, there is an antenna as well. That antenna can also be modeled as a resistor. For circuit engineers who are designing antennas, they will assume a model for a resistor, antenna as a resistor, and then design their circuits. That's it. So you don't have to know the mathematics of an antenna, the electromagnetic. Just you see, there are electromagnetics engineers who will design the antenna for you. As far as circuit designer is concerned, he will tell me, this electromagnetics engineer will tell me what is the resistance. So then I'll use that resistance in my circuit design and design my amplifier. That's how I'm going to do. So for practical loads, for example, as far as your iron box also will look like a resistor to the plug, right? If you're plugging into the supply and then deriving power out of it, your iron box will look like a resistor to that. Or if your water heater coil is also a resistor. As far as the circuit is concerned, circuit engineer who designs it is concerned, he is going to model it as a resistor and analyze it. So a load resistor captures finite power being delivered to it. So that's why we model it as a resistor. Yeah. Generally, as we will see, sometimes your RL will be infinity as well. If you are driving a capacitive load, your RL can be infinity. I'll slowly introduce that one by one. I don't want to introduce all of that in one lecture. We'll slowly go. But right now, we can assume RL as the load resistance. Okay. So for an ideal transconductance amplifier, if a transconductance amplifier is ideal, what should be the ideal values of Rin and R out? See, for a transconductance amplifier, input is voltage, output is current. Okay. Since output is current, ideally, you want all your current to flow into the load resistance. You don't want any of your current to flow into its own output resistance. Okay. So let me see if I figure it here. So, or let me just redraw it here. So if there was an output resistance, here, R out, okay, ideally you want all the current this transconductor is generating, which is Gm times Vn, to entirely flow into RL. For that to happen, what should be the maximum ideal value of R out? If you want all the current GMVN to flow into RL, what should be the value of R out? Is that okay? It's infinity. Is that clear to everyone? It should be infinity, right? Because if it is infinity, then it offers maximum resistance, so no current will flow, all the current will flow through RL. Okay? So that's the point. So for an ideal transconductance amplifier, you need R out to be infinity, and input is a voltage. So you want all the input voltage that you apply, Vs, to appear across the amplifier. So none of it is wasted. Okay, if you don't want, if you want the entire input to appear across the input of your amplifier, okay, then Rn should be infinity. Now voltage gain, see, I am talking about in the presence of RL. In the presence of RL, for an ideal, see, generally you will always have an RL in parallel with the load. In that case, it will be GMRL. It won't be infinity, it will be GMRL. Okay, the intrinsic gain, yes, it is GMR out. Intrinsic gain is infinity. Yes, intrinsic gain is infinity. True. Intrinsic gain is infinity. The loaded gain will be GM into RL. That will be the maximum gain. Okay. Intrinsic gain is infinity. Yeah. Okay. Fine. So fine, guys. We have 10 minutes. I'll quickly take you through, arrive at a model for a BJT, and then we'll start the discussion. So let's say I give you an IV characteristic that looks like this. It is 0 for V less than 0, and for V greater than 0, the current is a constant and value is equal to I naught. So if you are asked to mathematically represent this as a circuit, what will you say? For V less than 0, what is the mathematical model? Current is always 0. So what will be the mathematical model for it? Two-terminal model. Open circuit. Is that okay with everyone? For V less than 0, if current is 0, then it's an open circuit. So because this is the model for it. If you don't have any current, that's an open circuit. For V greater than 0, can I say it's a current source? Because for no matter what the voltage is, the current is always constant. So for V greater than 0, it's a current source. So that's how I've written it here. I is the, so look at the direction, direction of I have shown it in this direction. So it is, I have shown the direction of I naught this way. Okay. And V is the current through this. Now, if I give you a graph like this, I'm going to give you a graph like this. Instead of it being a constant, there is a slight increase, which means what is it? What does this tell you? If you increase your voltage, the current is also increasing little bit. Okay, from its nominal value of I naught, it's increasing. So if you are to mathematically express it, I'm telling you the slope of this line. The slope of this line is 1 by R. So if you are to mathematically represent this, what will be the equation in terms of I and I naught? See, I want to write, can I say it's a linear equation? Can I say it's of this form? I equals mv plus c. Right? Y equal to mx plus c. It's of this form. Y equals mx plus c. Yes. So I'll come to that. So now what is the constant? When V equal to 0, your current is I naught. So when V equal to 0, your I equals I naught. So the constant C will be I naught. So your I will be I naught plus mv. What is the slope of this line? Slope is 1 by R. So you get I equals I naught plus V by R. So if I want to represent this in a circuit, how will I represent it? I equals, see, this is the equation you have. You have two parts. So this is I naught and this is V by R. So by putting a resistor in parallel with the current source, I can capture a characteristic like this. So this tells me if I increase my voltage, the current will also increase slightly. That can be captured by putting a resistor in parallel with this current source. Okay, we will later see how to design current sources in this course, how to actually design and implement a current source in this course. At that time, we will see most practical current sources will exhibit these characteristics, what I have shown here. As you increase your voltage, current will also slightly increase. That's what you will expect out of it. Okay. So if I ask you what is the resistance, output resistance of a current source, ideal current source, what is the resistance? If I ask you what is the resistance, what will be the answer? An ideal current source, if I ask you what is the resistance of a current source, it's a two-terminal device, right? For any two-terminal device, the procedure is same. No, it's not 0, right? Infinity, right? Infinity. No. See, for example, how do you find resistance for any two-terminal device? Let's say I give you a two-terminal device to you. What will you do? You'll apply a test voltage and measure the current. In the process of measuring the impedance, you will short circuit independent voltage sources, open circuit independent current sources. So now if I open circuit this and look and try to look here, what will be the output resistance at this point? Infinity. Infinity. So for an ideal current source, the output resistance is infinity. For a practical current source, it will have a finite output resistance. So in this example, if I ask you what is the output resistance of this current source, what will it be? R. That's it. So this is a practical current source. So a practical current source will have a finite resistance given by R. Okay. Now you know that this is a mathematical model for what? If your current is increasing with some other voltage Vx, then what is the mathematical model for this? This is another IV characteristics. What is the mathematical? VCCS, voltage control current source. So you're already aware of it. So voltage control current source, I told you it's a 4-terminal device. The current varies in proportion to some other voltage. Voltage is between two terminals. This is the mathematical model. We don't know if this has input resistance or not, but some voltage. I can model some input resistance also. But the voltage, the current here will vary in proportion to the voltage between these two terminals. That's the mathematical model. It's a transconductance amplifier, a VCCS. Now, if I give you a characteristic like this, look at this current source. It is actually slightly increasing and varying. In this case, what do you think will be the mathematical model for this? Look at this. This is a transconductance. Okay. Not variable resistance. You will have a resistance in parallel. Yeah. You will have a resistance for every circuit. You will compute the resistance and it will come in parallel. So the same model with a resistor in parallel. A VCCS with an R in parallel. It's the same way. If you provide a resistance in parallel for a current source, same way for a VCCS also, voltage control current source as well, I'll have a resistor in parallel. That's it. So this is the way, this is the mathematical model we have developed for a characteristic that looks like this. Now if you are given a characteristic that looks like this, in this region between 0 to VB, I discussed this yesterday, 0 to VB, I can say that it behaves like a resistor, a variable resistor whose value depends on Vx. So this is Vx1, Vx2, Vx3, Vx4 and so on. So it behaves like a resistor between 0 to VB in this region. What about the behavior in this region between VB to Vmax? What is the behavior? What kind of a model will accurately capture it from VB to Vmax? A VCCS with, that's what we just discussed before, right? This is the same model here. A voltage controlled current source with a resistor in parallel. That's it. So in this region, I'm going to model a voltage controlled current source with a resistor in parallel. Do you guys recognize this IV characteristic? Which device do you think has a IV characteristic that looks like this? I0 versus V0. I versus V. Do you guys recognize the IV characteristic like this? In devices, they must have taught you MOSFETs and BJTs as well. Both BJTs, JFETs, MOSFETs, all of them will have similar IV characteristics. Okay? What is the name for this characteristic? There is a name. See, you remember there are two kinds of characteristics. Output characteristics, transfer characteristics. What is this? This is output or transfer? Think again. What is transfer? What is output? This is output characteristics. I'll come to again. You should see there is a subtle difference between output and transfer characteristics. So we take a BJT, a 3-terminal BJT device, a base, collector and emitter. It's a 3-terminal device. Generally, we'll assume base emitter as the input, VBE as the input, and the collector current IC as the output. That is generated in response to the input voltage VBE. So IC to VBE, this is the transfer, right? That's your transferred characteristic. VBE is the input, IC is the output. So that's like a transfer. IC versus VCE is your output characteristics. At the output terminal, I'm looking at it. IC versus VCE is output characteristics. IC versus VBE is transfer characteristics. Explain VCCS is in parallel with R again. Okay. See, did you understand till this point? If I have a current source with a slope, I can model this current source with a resistor in parallel, right? Is this fine? A current source, if I have it, yeah. So then the same thing, I said, if you have a graph that looks like this, where the current is increasing with voltage, then it is the mathematical model for this guy is a transconductance amplifier, a voltage controlled current source. It's a current source because it's independent of the voltage across it, right? Even if the voltage is changing, the current is fixed, but it is dependent on some other voltage, Vx. So that's why I modeled it as GMVx as a current source. Now what I'm doing, each current source I'm modeling it with a finite resistance. Okay, that's what I've drawn it here. This same current source now has a slope. So now previously for a single current source, when it had a slope, we modeled it with a current source and resistor in parallel. In the same way, for a transconductance amplifier, transconductance VCCS model as well, if it has a finite slope, then with a slope given by 1 by R in this example, I can model it as a transconductor and resistor in parallel. Same way as the previous example. Yeah. Okay guys, I think we are done now. See guys, can you just quickly tell me, will you be, okay, I think I'll discuss this. Will it be, because I'm going very slow, I have to going step by step in this course. So will it be free today or tomorrow for an extra class at 6 o'clock? Because I think today. No, does anyone have lab today at 6:15? Oh, no labs this week. Okay. Oh, you have a class today at 6. Class till 7. So tomorrow you guys are free. Whoever doesn't have a class, you are all free tomorrow. Can I take it on Saturday? No, Saturday, already we have one class. Saturday, right? I didn't want, it's a leave, it's a holiday on Saturday, no? So I didn't want to take it on a Saturday. Okay, so I'll decide that. Yeah, Saturday, generally, a lot of students, it's a holiday, right? You guys have 6 days of classes, so I didn't want to take it on Saturday for that reason. Okay, guys, I'll let you know. See, even if you can't attend the class, I'll post the video, so you watch it. Yes, I'll upload all the lectures, everything. So in case you have a class, some of you have a class and miss it, you can always watch the video before you come for tomorrow's class and the Saturday's class. Okay, I just want to one lecture I want to spend on the characteristics of a BJT. So that is why I wanted one separate lecture for it. And once your understanding of a BJT is complete, on Saturday I'll solve only problems. I'll show you how to solve a problem in a BJT. Or can I upload a problem set and you guys will be able to solve it yourself? See, I was teaching electrical sciences long time back to 2016-17. I wrote some slides. So those slides will contain almost every problem related to BJT. See, other section you have to be in my classroom. No, Moodle I can't do that. Because there are 2 sections I can't do that. Okay, so let me just stop recording. I think guys, I'm done with today's lecture.